So the next problem that we're going to look at for the practice exam is problem 2.62. And if you notice, the actual thing that they're asking for sounds a lot like the last problem. We're asking to express a force in terms of its Cartesian vector. But the key difference in this problem is that we're not dealing with a two-dimensional force. We're dealing with a force that's expressed in three dimensions. And particularly, we're given a magnitude and we're given some angle information. So when you think about actually describing the direction of vectors in 3D, we talked about three different approaches in chapter 3 of the text, or chapter 2 of the text, I guess, since this is a chapter 2 problem. The first thing that we talked about was coordinate direction angles. And remember, whenever you define an angle, it's nothing more than the separation between two line segments. So you can always think of just holding your fingers like this. And however you orient your fingers, right? Notice there's always a planar angle between those two fingers. And that's all that a coordinate direction angle is. It's a measurement of the angular separation between a coordinate axis and the line of action of a vector. The other thing that we talked about was kind of an elevation and azimuth-based description. I did an example of this in the chapter 3 homework review on Tuesday. And the third that we kind of talked about is describing the orientation of a vector in terms of a unit vector that was created from a position vector. So clearly, you can tell that this is an example where we're given geometrical information in the form of 1. Namely, this 50-degree angle represents the angle between the x-axis and the line of action of the vector, so that's alpha. This 60-degree angle represents the angle between the y-axis and the vector, so that's beta. And we're not given any information about gamma. So really, what this problem boils down to is if we're given that the magnitude of this vector is 450 pounds, that the coordinate direction angle for the x-axis is 50 degrees, and for the y-axis is 60 degrees, how can we basically, what we ultimately want to do is write this vector in Cartesian form, which means just decompose it into x, y, and z components. But in order to do this, we're going to need to find gamma. That's what we'll find. So the first question is, how do you actually find gamma? Well, what is the relationship between alpha, beta, and gamma? You might remember that if you take the squares of each of the cosine direction angles and you add them up, they sum to 1. And this is related to a property that we're going to look at in a minute, which says that if you know the magnitude of a vector, you can decompose it by just multiplying the magnitude by each component by its direction cosine, which is the cosine of these actual coordinate direction angles. So this is a formula that we talked about in chapter 2. If you need to review it, feel free to go back and do so. But if I solve this for the actual coordinate direction angle that I want to find, which is gamma, so I'm going to begin by, rather than trying to solve for gamma, I'm just going to solve for the cosquared of gamma. So isolating that on the left side of the equation, I get this formula, and plugging in the values that I have, I get this. And one thing that might confuse you, and it's okay if it does, is if you see something written like cos squared of 50 degrees, don't forget that that's the same thing as cos of 50 degrees squared, right? That's just a different way to write. So all that we need, let's actually start by just trying to compute what's on the right side of that equation. So you can see this is another video. I have had bad luck tonight. I keep having to re-record stuff. So I'm going to take 1 minus, I'm going to compute whatever the cosine of 50 degrees is, and then I'm going to square that. And I'm also going to compute whatever the cosine of 60 degrees is, and I'm going to square that. And I'm going to subtract both from 1. And I'm going to get an answer there of, to the full precision of my calculator, 0.3368. So using that same idea that I talked about on the right of what cos squared gamma really means, it really means cos gamma squared. The way that I'm going to be able to express gamma, and I'll go back to my .cam here in a minute, is as the inverse cosine of the square root of 0.3368. But what do you remember about the square root? So here's what I was actually just writing here. Hopefully you remember that whenever you take the square root, like what's the square root of 4? Right? What number do you multiply by itself to get 4? Well, it could be plus 2, because 2 times 2 is 4, but it also could be minus 2. So we need to consider both of these. And we'll see why we have to consider both in a minute. Imagine you just took the positive square root of that value. If you just said, oh, I take the square root, and if you've never used a software like MATLAB before, your last answer is stored in a variable called ANS. So notice if I take the square root of that actual value, and then I take the inverse cosine of it. So I'll say cosine D of, I'll actually type the whole thing in. Notice I get 54 degrees. So that would be what would happen if, going back to my .cam, if I took the principal or the positive square root here. So I took the inverse cosine of the square root of that number. So think about what we really want here is the angle actually measured from the positive x-axis here, right? So if you think about, let me actually just show you the other one. Clearly, when you look at that visibly, it's going to be more than that 54-degree value that we just computed. So the question is, what would happen if you actually took the inverse cosine not of the positive square root, but of the negative square root? In that case, you would get 125 degrees. And if you sum these two things up, what you notice is that they do sum to 180 degrees. And really what you're getting when you're getting that 54-degree angle is an angle measured from the negative z-axis. And when you get that 120-some degree angle, you're getting an angle measured from the positive z-axis. And in order to use this next formula that we're going to show, which is that you can always decompose a vector in terms of its magnitude times the cosine of the direction angles. For this formula to be valid, the direction angles have to be measured from the positive axis in each case. So if you notice here, just by visualization, the particular value that we're looking for here is not the plus square root, it's the minus square root, because that's the one that's going to give us the larger 120-degree angle. So just kind of writing in the results that we've have here, since I'm probably going to scan these, we'll take the negative sign. And what that's going to mean is that our gamma is actually going to be 125.4748 degrees. So when I plug in and I'll go back to this in a second, take the magnitude, which is going to be 450 pounds, and decompose by the cosine of all those coordinate direction angles. What I'm going to get is, and I'll just write it in here directly, and I'll use the vector capability of MATLAB to give me all my answers at once. So if you notice the x component, I'm taking the cosine of the direction angle, which was 50. Same thing for the y component, but use the y coordinate direction angle. And then for the z component, I'm going to use that value that I just calculated. So all that I'm showing you here is that's exactly what I'm typing into my calculator. And if I execute that and round to three significant figures, I will get an x component of 289 pounds, a y component of 225 pounds, and a z component of minus 261 pounds. Now you might ask yourself, well, what if on the test I forgot that when I take the square root, I could have a plus or minus combination? Well, what would happen in that case is you wouldn't get a negative z component. However, just by visualization, you know that this z component has to be negative. So hopefully that would kind of jog your memory, and you would say, oh, what must have happened when I took the square root is I'm getting the angle measured from the negative z-axis, not the positive z-axis. So if you were to be given one of these questions on the test, just make sure that your final answer, when you express this vector in Cartesian form, that it's consistent with the actual drawing that you see.